All right, so we have some results here, and printed in the console, it's kind of nice and neat. I'm going to go ahead and exit out of here for the moment. Printed in the console is image integration. I'm going to go ahead and copy what we're seeing here on the screen because this will actually be useful to us for just a moment. Here's the summary of all of those weights. I'm going to copy this selection and just put it into a new, let's just do Notepad here. And I'll paste them in here so we have them. So these are the weights of each that are assigned to each image. Now you notice one of the images has 1.0. That was the reference frame, April 2nd, number 2. And a funny thing is that you'll see that there are images that are both have higher weights and lower weights. Remember, this is relative. So the image that I picked that I thought might be the best frame, actually by the numbers calculated looking at the stars, isn't truly the best frame. Looks like the actual best frame by starlight might be one of these that says 1.3 here. That's a pretty good frame, looks like. So that frame by stars, not by gradient, but by stars, is the best one. Something on March 19th. Cool. And what we're going to use is this information because we can now, in image integration, we can combine the data in the normal way, and then we can also combine the data with now these newly adjusted files, and we can see the differences between the results. That's what I'm going to do here in image integration. So let's just use the output of the script. These are the outputted, they are adjusted files. You'll notice here at the end they have the NSG designation. If I look in the directory, you're actually going to see that there are NSGs here at the end of the files. Here are the original ones. But notice something else. There's also these little gradient files. So before I go combine, let me just, because I promised I would do it, I'm going to show you the gradient files as well. And again, I need to get into the, oh, that is the correct directory. Sorry, let's go back there. So I'm going to do star grad star. So here are the gradient files that were just outputted, and we can display them. So these are the gradients in each of those target frames. And it's kind of cool to be able to see what they look like, to see that they do actually look very similar to what we were seeing when we blinked through the frames. And there we go, you know. And they look very smooth and very similar to what we were seeing. So this can be diagnostic of making sure that things are working correctly. If I saw some bright little node here, I mean an actual something that isn't representative of what we were expecting the gradient to be, then of course we can go back and try to understand what we need to do to make the adjustment. And that's the kind of stuff I explain in my more formal tutorials. So I'm going to close these here. And we're going to look one more time at this list because there's something else that's very interesting. You'll notice that some of the frames are X'd out. That has to do with the setting. It's a default setting here. It's actually a recommendation that I made. But you'll notice that there's a minimum weight requirement. Well, it's not a requirement. It's all optional, right? But if you had to multiply for an equal frame, if you had to multiply that frame by more than a factor of 2 for an equal exposure to get up to what the reference frame was, it's probably a pretty crappy frame. It's not a very good high quality frame. So you can make this minimum weight whatever you want, but this refers to not the reference frame actually. This actually refers to whatever the best frame, after you compute all the weights, whatever the best frame is. If it doesn't meet 50% of whatever the weight is of the best frame, then don't include it here in the list when we load it into image integration. You can always turn them on, and we can look at them by blinking them, which I'll be doing in a moment for demonstration purposes. But this is the reason why we have some here that are X'd out. I'm going to do something kind of interesting. I'm going to keep them on. I'm going to demonstrate to you that even keeping the worst possible frames is still better than what potentially the default gives you in PixInsight when you use image integration through noise evaluation. So I'm going to turn them all on here. It did the right thing by unchecking them, but I'm going to check them. Now, in order to make this comparison I want to make, I'm also going to stick with whatever my reference frame was, just so that you can see that I'm being consistent in every possible way. So here was that reference frame, and I just set it to be my reference. It's not useful now, but it'll be useful in a moment when I do it in the default method, the normal way. Let's look at why this is not the default way. If you look in image integration, you'll notice that the setup is a little different. Now, normalization here is set to none. Again, the script loaded image integration for us. It's doing that for us here. It loaded the keyword here to be the weight keyword, to be n weight. And then this is the output normalization, which I explain in my tutorials at Atom Block Studios. But then there's the normalization that is for pixel rejection specifically. And again, you'll see that there is no normalization set here. Now I have the rejection algorithm set to be the generalized, extreme, studentized, blah, blah, blah. And this is fine. I'm just going to go ahead and leave it. It doesn't matter for purposes of this demonstration. So the settings should be something reasonable. These are actually the default settings, so they're reasonable. They're fine. That's it. I can now press this button and get a result. We can get an integrated image. And then I'm going to set it up with the original files that were not normalized through the script, and we'll combine those and we'll see the difference. But more important than seeing a visual difference in the frames is to see the difference in the weights. That is going to be, I hope, the most persuasive thing about this script. So here we are. We have rejection taking place. I'm going to keep this around just for a moment. And I'm going to call this, I'm going to add the word NSG here for my rejection here. And here is the resulting image. Now, let's do the other way, which is the following. I'm going to clear these, and I'm just going to add, now this looks all crazy complicated because we got all these extra things, but what I want is to add the files that are the original files. That's these. All of the new ones I'm not interested in now. These are the original ones. This is what you normally would have done with image integration. Normally, you would say, yes, we do want normalization. We would do additive with scaling. And then we would say, yes, we want noise evaluation here. Then for pixel rejection, we would say, yes, we want our scale plus offset, 0 offset here. And that should be it. That now puts us back into the regular mode. Again, I'm going to select the same one because I want to compare these images. So I want to select exactly the same file to be our reference here, set reference. And then let's do a combine at this point. Now I got to make sure, I'm going to pause. I did make a mistake. Now I think I did it right, so I'm going to go ahead and do it. Image integration here. Let's give it a moment to do that. And we will see a difference in these two images. Again, what we're looking at here in this version, which I should name once we get the other one, this is the gradient of our reference frame, which is fine. It's not a terribly complex gradient. So this is going to be our normal rejection high. So we'll say normal here. And I'll put this down here. And then I'm going to call this integration 1, but we'll call it normal. And then this one we're going to call NSG. There we are. So we can compare the two. Now what we can do is blink them. So what we're looking at here is the combined integration of all those frames. And because we are in no way are we compensating for or simplifying those gradients, the additive kind of convolution of all those gradients decreases the contrast actually of the image. So if we now combine, or excuse me, not combine, but blink the two, you hopefully can see that just because we're now simplifying the gradients, we're not removing gradients, but just by simplifying, we get better contrast, right? Because now we're matching all of those frames, which I should show you. I really should have shown you that. Let me go ahead and do that. Let me show you what the normalized frames look like. I apologize that I didn't do that. Star, NSG star. We can blink the output. I showed you the gradients, but I didn't actually show you the actual files here. So we'll go by size. These are the adjusted files, and we don't expect them to vary much because they should now match. This is the idea of normalization, just like I showed in the video. They should match one another. You see how I blink through them and they're matching each other? Now you can see some variations, like look at this one here. You can almost see some banding in there, and I think I know what that banding is. It looks like it's clouds, but some of it in one of these frames here is probably air glow is what it is. But in any case, you can see that these are now much, much more similar. Even the worst frames here are now looking very similar to the best frames, and that is what allows better pixel rejection and better weighting. It means that the script is doing its job. Okay, good. That would have been really bad if I had totally forgotten to do that. So we compared the output, but again, even the output isn't necessarily, by looking at the image, going to give us the final persuasive bit. It is the numbers. And so I'm going to show you the numbers in a moment as well. But this is the goal, is to make this integrated result. And it is from here, using the NSG result, that we would go perhaps to dynamic background extraction and then get the best possible world by removing the remaining gradient that's in that image. I am curious about something. I'd like to see that if we look at the NSG here, yeah, you'll get a very different kind of pixel rejection because, let's see, am I displaying these in the, yeah, I'm displaying these with the greatest stretch here, because you don't have that evenly, you don't have the field that looks similar from one image to the next because of the gradient. So you get a very different kind of rejection. So let's blink these. And you can see, notice how the satellite, let me zoom in here and show this to you. Because of the gradient, the satellite trail is not rejected as cleanly as when you have normalized the images very well. Do you see that? And you also get other, I won't call them artifacts, but we get some kind of extra, rejection because we're looking at these unaltered gradients from image to image. So you get a different result. NSG is what's going to give you, this script is going to give you a better pixel rejection result. And again, all of this goes towards improving the quality of your images. So now let's do this final thing. I'd like to look at, again, here, let's look at what the normal method calculated. When I just combined it in the normal way, I have weights. It spit out weights here. They're all right here in the console. If I scroll up, I'm going to find the weights for any particular image that we just worked with. See how it says weights here? But let's look at what we gave weight to, right? It says that, let's compare. And remember, I set it to the same reference, so they should be relatively the same. Let's look at one of these poor images. What's an image that's, I don't want to look at the worst one. Let's just pick an image that's not maybe the worst, but it might be something that, we still want to use. So this image here says that this image is should be given a weight of 0.75 compared to our reference frame, right? So it's not quite as good as our reference frame is what this is saying, according to NSG. Now, let's look at the same frame, and I'm picking this randomly. I don't know the answer. Let's look at the same frame. So we go Abel 66. This is March 19, number 7. Kind of makes sense. It's the end, the last few frames, maybe when it's lowest in the sky. So we want March 19, number 7. So we scroll up here, and we're looking for March 19, okay, that's 1. This is March 19, 6. March 19, number 7. I am pausing, I hope, with dramatic results here. It is because, that says, let me just say what this says. That says that this frame, according to noise evaluation, with its own statistical means of calculating this term, which is like a scaling factor, in combination with that noise result, it gives a weight that says that this image should be 4 times as good as our reference frame. Again, I just said it right here. If I scroll up to, I mean, I can do my due diligence here. If we scroll up to whatever April 2nd is, number 2, we should see that it says a weight of 1. Where is April 2nd? Hold on, let me find it. Okay, so here it is. Indeed, it's all using the same reference. April 2nd says it has a weight of 1. So now let me scroll back down here. I just really want to show this to you. This is saying that it would have been adding in this image, which is a worse image, and there are worse images that are even getting higher weights, okay? It would have added that in for more than the best images in the set are worth. And that, to me, that is not optimal. And I'm saying that with kindness. So I hope that you can see here that using, let's call it outsourcing, the normalization process to normalize scale gradient, that script, it has a number of benefits, and those benefits are, they are paramount. And I hope that in looking at this video, you found it persuasive. Give it a shot. See, it's early days. It very well could be that there is something about this script that I am not appreciating, but at the moment, this is exactly something that I've always wanted PixInsight to have. It is a measure that looks at the signal in some robust way, and hey, John Murphy did it. He made this normalized scale gradient, and so far it has been a really fun resource to use. You know, I'm back again. This is going to be kind of like an encore. Maybe you look at these numbers and you go, okay, well, those are just numbers. Does it really matter? I didn't actually show you that. Let me show it to you. So we can compare the reference frame to this frame itself by blinking, right? This frame was March 19th, and it's number 7. So let's look visually at these two frames. Let's decide with our own eyes and our own brains which of the two frames is better. We should be able to do that. We can look at numbers and say, oh, numbers. But in this case, our eyes and brains do a pretty good job as well. So we'll load 2 frames. We'll load that reference frame, which we know. Now, the one I want to load here, these are the original ones. So we want to look at the, what kind of order is this in? Okay, we want April 2nd, number 2, which is, let me find these frames. I was looking at the NSG files again. Can't seem to keep it straight. So April 2nd, number 2, 1, 2, here. That's this frame. And then we want that March 19, number, I think it was 19, number 7. So March 19, number 7 is this frame. I will double check that, but those I believe are the 2 frames. So let's check that. Yes, March 19th, number 7. 2 frames we were comparing. Noise evaluation in the normal way says that that frame is better. Let's see if that's true. So which of these 2 frames is better? Is it this frame or is it that frame? Which of these 2 frames is better? Just ignore the gradient. Just look at the nebula. Is it this frame or this frame? It's not just the gradient. I want to specify that. You can even tell by the number of stars that they're, in addition, that gradient is probably caused by thin clouds. So there are fewer stars, the signal is less, everything about that image. This image is a poor quality, and yet noise evaluation said it was the better image by far. So, gosh, if that does not button up why for some data, I think for many data sets, unless you are under pristine sky with no light pollution and all of that, the normalized scale gradient is the way to go.